Hello everyone, welcome to the biggest ideas in the universe. I'm your host Sean Carroll. We are here for the Q&A video for idea number 19, which is probability and randomness. But first, elephant in the room, the real news here is haircut has happened for the first time in the pandemic. Real professional haircut, not personal haircut. We had someone, a friend of ours, come over actually to our house, wore masks and everything, very, very responsible. But now, okay, hair's looking more normal, a little bit less scraggly. You know, I have mixed feelings about this. I kind of liked the scraggly academic look, but, you know, there's something to be said for gravitas and professionalism also. Of course, the next two regular videos in the Big Ideas series were already recorded before the haircut happened. So right now you get to see the haircut, but the next two videos I'm as scraggly as ever. Sorry about that. So today we're supposed to be here for the probability and randomness Q&A video. But to be honest, there weren't a lot of questions about probability and randomness. There were questions, of course. There are always questions. Lots of people like to ask questions about lots of things. If you ever do want to ask questions about things that are not about these videos, the trick is to become a Patreon supporter of the Mindscape podcast, and then you get to ask questions at the monthly Ask Me Anything, and then I will do my best to answer every single question. But here I like to try to keep the questions about the topic of the video, and really there were almost no questions about the actual subject of probability and randomness. So this is going to be a short video today. What I'm going to do is take advantage of that extra time, and I'm going to make an extra little bonus video, which is not about physics at all, but about how I make these videos. I already did a little bit of an explanation for that. That was buried in the Q&A video for force and energy and action, and so no one sees it if they don't watch every single video. So a lot of people have emailed me asking, you know, what is the technology, the software, and whatever. So I'm going to make another video about that and post that separately. That's what I'll do with the extra time for this shortened video today. What there were a lot of questions about, but, you know, I don't have a lot to say about, was Norton's dome, okay? So we do want to talk a little bit about Norton's dome. And Norton's dome was supposed to be an example of how classical Newtonian mechanics can fail to be perfectly deterministic for initial conditions that are set of measure zero. So they're there, but they're infinitely finely tuned. And the idea was you had a dome. I'm not going to draw the dome very well, but you could sit a ball on top of the dome, and then it could roll down. And if the height of the dome was a very specific form, r to the 3/2, height is measured sort of downward. And r, by the way, I mistook. I said that r was just the radial distance in the plane, but r is actually this distance on the dome, okay? Tiny little difference. It doesn't really make much of a difference, but just if you should try to get things right, okay? And so the point was you can solve this. Of course, there's a solution where the ball is sitting right at the top of the dome and never ever moves. But there are also solutions where the ball can sit at the top of the dome for arbitrarily long periods of time, for literally any period of time, and then start rolling. Okay, and so the time at which it starts rolling is not determined by the initial conditions. If the initial conditions are simply the ball is sitting stationary at the top of the dome, it can stay as long as it wants, or it can roll at any time. So Norton actually first introduced this as a way to question whether or not causality is a perfectly good concept, well-defined in Newtonian mechanics. We're not really about that today. It's more about the determinism aspect that we were interested in. But, you know, it turns out, I didn't really get into this very much in my researches. I knew about Norton's dome, but I didn't want to make a big deal of it. I just wanted to give it as a cute little example, and in part to compare with quantum mechanics. But people get very emotional, it turns out, about Norton's dome. People don't like the idea that classical mechanics might not be perfectly deterministic, or at least that this is a counterexample. So let me just, and I have very little to say about that. You know, I don't get emotional about this myself. It's, you know, it's not, for one thing, classical mechanics is not the real world, right? If you're a mathematician and you want to solve, you know, you want to understand the space of solutions to different differential equations, then by all means, I understand why you should care about this. But if you're a physicist, Yeah, classical mechanics has its properties, but they're not real, so who cares in some sense? I mean, it's good to know what the properties are. Here, the answer is there's a set of measure zero, infinitely unlikely to be chosen randomly in the set of all possible initial conditions that do not seem to be deterministic. So let me just explain a little bit more about what's going on here. If you solve, the point is you're solving Newton's equation of motion, F equals ma, which is m dv dt, right? Where v is the velocity, which is m d squared x dt squared. Or you can, and rather than x, you can choose r, okay? So the point is that the force needs to be zero even when the ball starts moving. And how can that be true? Why would the ball start moving if the force is zero? When you're sitting at the top of the dome, you're sitting up here, there's no net force acting on you. There's a gravitational force pushing you down, but the dome has a responding force that is pushing you up in exactly enough way to compensate. So there's zero force on you. So naively, you look at this equation and you say, well, there's no force on you, there's no acceleration, you don't start moving. But what Norton did is he carefully chose the shape of his dome so that there's a solution that looks like r is proportional to t minus t naught to the power of 4, okay? So what does that mean? So the point is, the reason why he chose this r equals 3/2 up here is that when you get the solution to figure it, you differentiate the potential energy to get the force, plug it into this equation and so forth, then you find that this is indeed a solution for any value of t naught. That's the point, okay? And what's going on here is if you plot, so here is r as a function of t, okay? And we'll just use different colors to make it very clear. So the solution is, oh, actually, sorry, what I should say is, let me be a little bit more clear here. Yeah, let me be more clear here. So let me just erase this. The equation is right, but I need to say something else. The point is that there's a solution where r equals this, for times after t naught, and r just equals 0 for times before t naught. In fact, equal to, because it's the same at t naught, okay? So that's the point. That is what makes this all special. If we plot r versus t, then our solution looks like, let's take t naught equals 0, just to be very, very simple about it. In fact, let's make our pen a little thicker so it's easier to see. And so the solution looks like this. R is just 0, and then at t naught, it starts moving like this, okay? So to see why this is possible, think about, forget just that t naught equals 0, like we just said, right? So r is proportional to t to the 4th. The velocity, which is the derivative of r with respect to time, goes like t cubed. Therefore, the acceleration goes like t squared. And again, this is all t greater than or equal to t naught, which equals 0 here, okay? Everything is 0 before t naught, before 0, and then everything becomes these curves. So then the jerk, remember the jerk is dA dt, which goes like t, and the snap, which goes like the second derivative of a with respect to time, goes like constant. So everything is very smooth and matches on very, very nicely at t equals 0, but something does happen, but something dramatic doesn't really happen until the snap, which is the second derivative of acceleration, or if you like, the fourth derivative of the position with respect to time, okay? So to make this clear, we could plot all these little buggers. Let's plot the velocity. Okay, well, velocity it's going to look very similar, to be honest. I cannot draw sufficiently carefully enough that you can tell the difference between t to the 4th and t cubed in my drawing. Likewise, guess what? That's the velocity. Here's the acceleration. It's going to look pretty much the same. Now it's t squared. Okay, these are all really different. This is t to the 4th. T cubed, t squared. The jerk goes linearly in t, and now we begin to see what is going on. So the jerk, come on, white. The jerk, as a function of time, is going to be constant, namely 0 before t, and then it's linear. And the snap is going to be discontinuous. So the snap goes like this. Constant, and then boom. And all this is just from taking derivatives of the initial function. And you might say, well, okay, that's what's going weird here. Your snap, your fourth derivative with respect to time, suddenly was discontinuous at t equals 0. And what that means is, I should have said this before, but if you just went up here and solved Newton's equation, F equals ma, this is Norton's original point. If this is all you're doing, you say, I give you the position, I give you the velocity initially, I give you the force, the potential energy function that you can differentiate to get the force, and then I solve it, right? So this is a solution, but for any value of t naught, it's a solution. So there's another solution that looks like this, where it's constant to some other time, and then starts going st to the fourth. And there's another solution where it started going earlier, right? All of these are perfectly good solutions. So the actual solution is not picked by the initial conditions. And then you would likewise shift all of these guys. So if you look in the literature, see what people say about this, there is a tradition that says, well, okay, you've obviously cheated because the correct physical allowed solutions are those for which all of the derivatives are perfectly continuous. So because the fourth derivative, the snap, is not continuous, this is a fake solution. This is not really good. And Norton, I think quite correctly says, wait a minute. You didn't say anything when you gave me the rules of the game about infinite continuity for all of the derivatives, okay? You just made up a new rule. And are you allowed to make up a new rule? Well, maybe, sure, why not? Go make up all the rules you want. But you don't have to make up that rule. You could just say, you stuck with the rules that Newton wrote down, right? And in that case, it's not deterministic. But again, my point was not actually to pick out, to sort of make fun of Newtonian mechanics, because Newtonian mechanics is not right. If instead you have quantum mechanics, h psi equals I times the time derivative of psi, this does not have any of that lack of determinism, okay? There's no even set of measure 0 initial data for which this simple first-order time derivative equation doesn't have solutions. Now, quantum mechanics has other issues with indeterminacy, as we know, as we've talked about, but that is a difference. And classical mechanics is not right. It's just supposed to be an approximation to quantum mechanics. So if your interest is in, again, mathematically, the behavior of different sets of equations, then by all means get worked up about Norton's dome. But if your interest is in, is the universe deterministic or not, Norton's dome says nothing about that, because it's about classical mechanics. It's not about quantum mechanics, which is the real world, as far as we know. Furthermore, I should say that Norton's dome is not the only example of non-determinism in Newtonian mechanics. Some people like to use the following example. I don't like it, but I'll tell you what it is. You have three particles that just come and they collide. Okay? Three particles, Newtonian mechanics, and they collide exactly at a point. And well, the point is that, they have momentum, they have energy that's conserved, and they can scatter off of each other at a large number of different angles and still conserve all the energy, conserve all the momentum, obey Newton's equations. It's also clearly a set of initial conditions that are of measure 0, because they're literally point particles. They're not little billiard balls, then it would be a different thing. They're literally points, so they have to exactly hit each other at the same time for this to make sense. That just seems like horribly singular to me. The forces when they hit each other are infinite, right? So I think in this case, it's safe to say this is just not really well defined. But if you want to say it's non-deterministic, that's also good. That's also okay with me. There's another example which I hesitated when I was thinking about the original idea video. I was going to talk about this, but then I realized I did not understand it myself, and so I didn't talk about it. Now that I'm doing the Q&A, I still do not understand it, but I figured I can just admit that I do not understand it. I can tell you about it if you want to read about it, and that is the famous Space Invaders counterexample. Oops, Invaders. So the idea here is you have space and time, okay, x, t, there you go. And you're doing Newtonian mechanics with gravity, okay? So there's a bunch of particles that exert inverse square law forces on each other. And there's a bunch of them. It's not just 2 or 3. There's like, I think you need 5 or 8 or something like that. And so you have a bunch of particles, at some initial time, and they're all doing crazy things. They're interacting with each other, blah, 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 blah. And the claim is, and again, I find this claim hard to believe, but it's a claim that someone makes, and they're mathematically careful, so probably there's something that I just don't understand about it. But the claim is you can arrange these initial conditions very, very carefully so that one of these particles interacts and it zooms off after these interactions, or the interactions never really end because it's a 1 over r squared law, so there's always some force being exerted. One of these particles has the property that it goes to x equals infinity before some specific time, t star, okay? So there's a time that this Newtonian particle, acting under the force of gravity, interacting with all of its friends, never reaches. It goes infinitely far away, infinitely fast. Remember, Newtonian mechanics, not special relativity. There's no speed of light rule here, okay? So this one particle can just zoom off as fast, infinitely fast, really, and it not reach the future. And then just like with Norton's dome, we can do the following thing. We can take this picture. Let's see if I can do this. It's always an adventure when I cut and paste in Notability. And I can turn it upside down. Now I can relabel. Okay, so just move the arrows. Point them the other way. X and t. And what I have now is, oops, my t is upside down here. So now the point is, again, it's still Newtonian gravity, and there's some time t star before which there's a certain number of particles. And then at t star, a particle zooms in from infinitely far away to join the particles that are already there. Okay, that's why it's called Space Invaders, because this particle here, I should have made a different color, but this particle here is zooming in from spatial infinity to join the others. And that particle was not there before t star. So you could not have predicted its existence by just giving me the initial data at any time before t star. Now again, I do not understand exactly the details of the proof that this is possible, but people who have looked at it claim to say that it's okay, so it seems okay. So this is a different kind of failure of determinism, but it is a failure of determinism. The failure here is saying that I don't know whether or not stuff is coming in from infinitely far away at arbitrary times. Now again, Newtonian mechanics is not right, so maybe you shouldn't be bothered by this, but certainly you shouldn't be too emotionally attached to showing that Newtonian mechanics is deterministic. Let's put it that way. So there are different examples about how Newtonian mechanics is not completely deterministic. Now, the other thing people said was, well, and I'm sure that I mentioned this in the video, but people said it anyway, you cannot possibly actually arrange the initial conditions in Norton's dome so exactly that it will literally sit there for an arbitrarily long period of time and then start rolling, either because of quantum mechanics or just because of imprecision in how you place the particle there initially, or because there's no such thing as a closed system and there will be, cosmic rays or air molecules or just photons buffeting the particle. So, I mean, the answer to that is, duh, obviously not. And this has to do with the bigger issue, which is worth getting into, of Laplace's demon. Laplace's demon says that if you knew everything, you could predict what's going to be in the future. And Norton's dome and the Space Invaders are both examples of how if you just take your rules to be classical mechanics as Newton wrote them down, Laplace's demon doesn't quite work. But maybe you could patch it up so that it works. That's fine. But there was this idea that Laplace's demon is undermined by chaos theory. So chaos theory is worth explaining. I did mention this, but let me say again what it is. Chaos theory is the idea that under certain conditions, for certain physical systems, small variations in initial conditions lead to large variations in final conditions. Now that I'm thinking about it, now I'm writing it down, I realized it's possible I didn't actually say this in the probability video, but I will say it in an upcoming video. This is a problem with doing the videos before, weeks in advance. So this sounds like a very loosey-goosey statement. What do you mean by small? What do you mean by large? But it's been made very, very precise. It means that the variations in the final conditions depend exponentially on variations in the initial conditions, okay? They do not depend linearly or even quadratically or something like that. So that's a literal quantitative way of making sense of the idea that any tiny variation in the initial conditions makes your system unpredictable if you don't know exactly what the initial conditions are. And so this, was a big deal when it was invented. Different people sort of came into the idea of chaos theory from different directions. Poincaré, who we've met before, was one of the people. He was trying to there's a long, fascinating story about Poincaré proving that the solar system was completely stable. And he wrote a paper, this was like a challenge. Like what they used to do back in the day was like the king of Sweden would announce a contest for the best mathematical essay. And then, the great minds of Europe would write their mathematical essays and it would be judged by somebody and the king would give you a prize. I don't think that happens anymore, but we have other ways of rewarding good ideas. So Poincaré wrote his essay and it won the prize and they were publishing it. And, as happens, you go and the editors read your publication and they give you notes and you try to correct it. And somewhere in the process of refereeing or editing, someone pointed out, there was a mistake. There was a gap in the proof that Poincaré had. And Poincaré was a smart guy. He looked at the comment, he realized it was correct, and he set out to fix it, and he ended up proving the opposite. He ended up proving the solar system is not stable. And this more or less can be thought of as the origin of chaos theory in some sense. There are other people like Lorentz, different Lorentz, not our Lorentz, had ideas that led to this kind of unpredictability. And so people have said that this idea of chaos theory undermines Laplace's demon. Okay, so forget about niceties of measure zero, like Norton's dome or Space Invaders or whatever. Chaos theory is just saying for generic initial conditions, for any initial conditions, if your system is chaotic, some systems are chaotic, some systems are not. It's easy, simple systems can be chaotic. You don't have to work very hard to make a system chaotic. For generic initial conditions for a chaotic system, if you don't know exactly the initial conditions, and by the way, you never do know exactly the initial conditions, then you cannot predict what will happen in the future, and therefore, the argument goes, Laplace's demon is somehow undermined. Okay. I've always thought and continue to think this is a completely nonsensical argument. I mean, it's a bunch of true statements, but it completely misses the point. Chaos theory, Laplace's demon says, if I know the initial conditions exactly, I can tell you what's going to happen next. Chaos theory says, if I don't know the initial conditions exactly, I cannot tell you even approximately what will happen next. Those two statements are not contradictory. They're statements about different initial assumptions, whether you know the conditions exactly or not. And people try to say, well, yes, but the point is you never know the conditions exactly, to which, again, I will say, duh, everyone knows that. Laplace's demon was never supposed to be a research program. It was never supposed to be like, let's build something that would be Laplace's demon. It's not really a statement about a vast intelligence who should be able to know things and predict things. It's a statement about the structure of the theory. It's distinguishing between a theory that is deterministic, from which the initial conditions predict the future, and other theories that are not deterministic, right? There are plenty of theories where you just can't, even in principle, predict the future from arbitrarily accurate initial conditions. And that's the point of Laplace's demon. Not that you could ever build it. And so chaos theory introduces a practical limitation on how close you can get to being Laplace's demon. But even without chaos theory, even if you just take like a box of gas with things bumping into each other, you can't come very close to being Laplace's demon because the world has too many moving parts in it. It was never supposed to be a practical kind of thing. So chaos theory is intrinsically interesting in and of itself, but it's not. Its interest is not because it overthrows the idea of Laplace's demon in any way. And likewise for, quantum fluctuations, etc. Okay, two more questions or topics came up. One was determinism, which we were talking about, versus free will. And I don't have a lot to say about this because I do have a lot to say about this topic in general. Read my book, read The Big Picture, or read Janan Ismail's book, How Physics Makes Us Free, or listen to the various podcasts I've done on this. But I just want to make one very brief point about this relationship here. The issue is, if we thought that we did live in a deterministic universe, if we thought that the laws of physics were classical, and Laplace's demon was correct, and we put aside sets of measure zero, and we put aside chaos theory and all that stuff, then how in the world can you think that human beings have the ability to freely choose what to do next? Human beings are made of stuff. That stuff obeys the laws of physics. The laws of physics are deterministic. Full stop. That's all you have, okay? Now, so some people say that the choice is between determinism and free will, where free will is interpreted as the ability to make choices, individual, human, autonomous choices, okay? The only point I want to make here is that that is not the choice. There's no relationship between whether the world is deterministic or not and whether or not you have free will or not, okay? The world can be deterministic and you have free will, or it can be deterministic and you don't have free will, or it can be non-deterministic and you have free will, or non-deterministic and you don't have free will. All those are absolutely legitimate intellectual positions. So when I say the world can be, what I mean is there are smart people who believe the world is like that, okay? I mean, obviously the world is one way or the other, but there's no in principle incompatibility between determinism and free will, nor, more importantly, is there some idea that if the world were non-deterministic, that would somehow help you have free will, okay? So let's be very clear about what I mean. If you're deterministic, then the question is, what do you mean by free will? And guess what? People don't agree on what they mean by free will. And this is quickly where it becomes the world's most boring argument to have, because I don't care what definition you use. The interesting question is not how you define free will, but how you deal with the fact that on the one hand, the world is microscopically deterministic. If it were, let's imagine that it were, okay? The world is made of things, atoms and so forth, that obey laws of physics, and you don't have control over them. But you don't know what the conditions of those atoms are. You don't know. You're not Laplace's demon, okay? You don't know what the position and velocity of every single particle in your body is. So what attitude should you take? And there's two attitudes you can take. One attitude is, what I care about is the in-principle question: could I sort of violate the laws of physics by my human volition? And if I can't, then I say I don't have free will. The other point of view you can take is, look, I would like to describe real human beings using the actual knowledge those human beings have, because what I care about is coming up with the best effective theory that I can. If you hearken back to the days we were doing effective field theories, right? I'm not doing the complete ultraviolet completion of the world. I'm doing an effective theory of human action. And human beings don't know positions and velocities of all those particles, so who cares about the in-principle determinism underneath? What I want to do is describe people as they are with the information they have. And it may very well turn out that the best way to do that is to imagine that those people are described as choice-making agents, right? As people who are able to take in information, think about it, make choices on the basis of that. That is called compatibilism. Compatibilism between determinism and free choice or volition or free will or whatever you want to call it, okay? Personally, as someone who believes in, emergence and higher levels, different ways of talking about the universe, I find the compatibilist point of view very compelling. I think, it makes sense. I don't know of anyone who denies free will who really goes all the way to saying, never mentioning the idea that human beings make choices, okay? Or that human beings should choose one thing or the other. Of course, they say all the time that human beings make choices, and then they say, yes, but I don't really mean it. What I really mean is that there's something going on underneath. If you say that human beings make choices and you really mean it, And you also believe that the laws of physics underlying everything are perfectly deterministic and you can't violate them. There's a word for what you are. It's called compatibilist. That's what you are. That's what compatibilists do. And so there's no, in principle, incompatibility in the space of all possible positions one can stake out between determinism and free will. But more importantly, I realize I'm not drawing anything. I don't really have anything to draw. Here's a person, okay, and they're thinking about things, and they're making choices. There you go. That's the best I can do to draw something. The much more important point I want to make is, what if the laws of physics were not deterministic? Okay? What if it was GRW theory? Remember we talked about all the different possible formulations of quantum mechanics. One of them are these spontaneous collapse theories, where truly unpredictably, the wave function of the universe just collapses onto locations of certain particles at some rate of probability per unit time, etc. Okay? So that's a theory, that's a whole family of theories, which is truly not deterministic. Okay? You cannot predict the future from the past because there's an element of randomness in the fundamental equations. Does that give you free will? No. Of course not. Why would that give you free will? There's some random possibility that an electron collapses at its wave function, therefore I can choose? No, that just doesn't follow at all. If you are not a compatibilist, okay, if you're not willing to say that I'm going to describe human beings at a higher level of emergent behavior with incomplete information, if you're just a hardcore microscopic describer of things, okay, whether or not the underlying laws of physics are deterministic or not has absolutely zero to do with whether or not you believe in free will. What it has to do with is, are there laws, right? If there are laws that human beings obey that are microscopic and reductionist, and you want to be the kind of person who says that excludes the possibility of free will, whether those laws are deterministic or not is completely irrelevant. The question is, do the human beings obey the laws, right? If that's going to be your attitude. So, again, determinism is not the thing that is opposed to free will. You can be deterministic or not deterministic. You can believe in free will or not, and all four of the little boxes in that grid can be filled up. So that's all I want to say about free will. I'm not going to tell you which box you should be in, but all the boxes exist, okay? That's all I want you to believe. Final question is, and this is, I have very little to say about this one, Bayesianism, which we did talk about, Bayesianism, so there's Bayes' rule or Bayes' law or Bayes' theorem, whatever you want to call it. There's an equation, okay? The probability of the theory Ti, given the data, is the probability of the data in that theory, the likelihood function, times the prior probability of that theory, divided by the total probability of getting that data over all different possible theories. Okay, this is the equation you use for updating your priors, that's your prior, to get your posterior probability given the data. Your prior probability that theory I is correct versus after you have the data. So this is Bayes' rule, and it's just true. This is just an equation. In fact, look, I can multiply both sides, and what you find is that the probability of the theory given the data times the probability of the data equals the probability of the data given the theory times the probability of the theory. And this, in fact, is just a mathematical identity. That's why Bayes did not have to work very hard to prove his theorem. Once you understand what the definition of a conditional probability is, this is going to become very clear. So the point is that this is not Bayesianism yet. This is just a theorem in probability, just a mathematical theorem. Bayesianism is kind of a philosophy of life. It's the philosophy that you should think about all probabilities in this way. And there's objective Bayesianism, which I just don't understand, and subjective Bayesianism, which says, I'm going to invent my priors. There might be smarter or less smart ways to invent them, but still I invent them. The motto is, everyone is welcome to their own priors, but not to their own likelihoods, okay? The likelihood function should be predicted by your theory. And then, you go through life updating your priors when new data comes in. That's the philosophy of Bayesianism. But this is true, these equations are true for anyone's philosophy of probability. There's mathematical theorems. And the question I wanted to get to was Bayesianism versus, although not really versus, compared to quantum Bayesianism. So you may have heard of this. I forget whether we've actually mentioned it. Quantum Bayesianism is one of the approaches to what we called epistemic philosophies of quantum mechanics. So in the epistemic approach to quantum mechanics, the wave function, psi of x, you remember? So psi, as we do it in Dirac notation, capital Psi, let's make it, is an element of Hilbert space, right? And if you were a many worlds person, you say that's the world. That is the complete description of reality, this wave function in Hilbert space. You can represent it as a square integrable complex valued function over the space of all configurations or something like that, but who cares? It's a vector in Hilbert space and that's reality. The quantum Bayesian says, no. This is not reality at all. What the wave function is a way of making predictions about observational outcomes. So the ontology, as the philosophers would say, if you're an Everettian, is a vector in Hilbert space. That's what reality is. If you're a quantum Bayesian, then the ontology is there are agents, and agents have experiences. And there's a rule for figuring out how you're going to predict the probability of having different experiences by starting with your wave function. The wave function to a quantum Bayesian is analogous to the priors in regular old classical Bayesianism. The wave function might be different for two different people. The wave function of an electron, a single electron, might be different in the minds of two different people because the wave function is a fundamentally subjective thing to a quantum Bayesian. And then it's some admixture of the rules of quantum mechanics for changing wave functions and the rules of Bayesian probability theory. So if you say to a quantum Bayesian, okay, but if the wave function isn't reality, what is reality? I have trouble understanding their answers. They don't ever quite tell you what the answer is. What they will say is that reality comes into existence through the mutual experiences of all the agents. It still doesn't tell you what it is, right? I've not quite gotten an answer as to what the reality is. Maybe a quantum Bayesian will chime in. But the question was, or at least my reading of the question that I saw on YouTube or wherever it was, how do these things relate to each other? If you're a good Bayesian, does that imply or suggest that maybe you should be a good quantum Bayesian? So no. I think that quantum Bayesianism is an ambitious, it's still, let's be fair to the theory. I have no special interest in quantum Bayesianism. It's just not my deal at all. I'm a realist. All these epistemic approaches are kind of instrumental. They're using quantum mechanics to make predictions rather than directly describing reality. I think that the way to make progress is to try to directly describe reality. And people have tried to mix epistemic approaches, saying that the formalism of quantum mechanics is about making predictions, with realist ontology. So you say, well, making predictions about what? And that attempt has completely failed, as far as I know. No one actually has a working theory where quantum mechanics is all about knowledge and probabilities, and reality is about something different, okay? So I like the idea that quantum mechanics is just about reality, full stop. Having said that, quantum Bayesianism is relatively new, right? Relatively youthful as theories go. There's a lot of smart people who put a lot of credence in it, as it were, have high priors that it is true, or high posteriors. And so I'm very happy that they're working on it, and maybe it will lead to some kind of breakthrough. You have to pick your battles when you're doing research in physics. And maybe this is a good place to stop, because I'm done talking about quantum Bayesianism, but this is a good big philosophy point to end the Q&A video on. Look, I remember being shocked when I was in grad school, because I was in grad school late 80s, early 90s. So this was after the first superstring revolution, which was in 1984. So certain people just fell in love with string theory. They felt that superstring theory was the way forward. Clearly, it was going to be the theory of everything. Soon we'd be predicting the mass of the electron, etc. It was great. Other people were incredibly skeptical. So I was a grad student at Harvard. I was in the astronomy department, but in the physics department, we had one young assistant professor doing string theory, but none of the senior faculty did string theory. Whereas other places like Princeton, were all string theory. And the number of major university departments that were dominated by string theory was small at the time. It wasn't very big. It wasn't until the second superstring revolution that suddenly everywhere had to have string theorists, right? But the point is I was going to get to was that so circa 1992 or whatever, before the second superstring revolution, I was still a grad student, and we had a visitor come to give a talk. And he gave a talk on certain dark matter candidates in superstring theory. And I said, well, I asked him some question that was in a related context that was not superstring theory. And he said, look, I don't care. My idea is to work on string theory, and I'm just not interested in ideas that are not in the context of string theory. And at the time, I was kind of outraged by this. I was like, oh, come on. How do you know that string theory is right? Maybe it's right, but it could be wrong. Now that I'm older and wiser, I'm much more sympathetic, even though my chance that string theory is right has not really changed one way or the other in the last 25 years or whatever. But the idea that you need to make a choice is something that I now understand better, a choice of what to work on. So you may very well think that the theory you're working on has an 80% chance of being true and a 20% chance of being false. But nevertheless, you choose to put 100% of your effort into working on that theory. In fact, you may only think that the theory you're working on has a 10% chance of being true and a 90% chance of being false. But you're saying, look, no one else is working on this theory. I think this theory has a 10% chance. If I'm right, it's hugely important. I'm going to ignore everything else and work on this theory, okay? And my point is that's a completely rational strategy to adopt. Because you don't have to spread your individual research or intellectual effort equally over all the different theories in the world. The field should do that. Science as a whole should do that. We should have people working on one theory, people working on another theory, as long as we're not sure which one is correct. But not every individual has to do that. That would be horribly inefficient, right? You have some people who bet one way and some people who bet the other way. And so when it comes to quantum mechanics and the foundations of quantum mechanics, there's a sense in which I do research in the foundations of quantum mechanics, right? I clearly do. I write papers on it, etc. But the community of people working in foundations of quantum mechanics get together and have all these meetings where they talk about all these different formulations of quantum mechanics, right? Bayesianism and GRW theory and Bowmanian mechanics, and they prove all these theorems, and et cetera, et cetera. And it just doesn't interest me, because my take on the foundations of quantum mechanics is that Everett is probably right in my mind, and what I want to spend my time doing is pushing that theory forward, understanding how that theory fits into what we know about the world. And that is so I'm just not that interested in people doing work in quantum Bayesianism, okay? But not because I think that they're wrong. I think that they're probably wrong, but they could be right, and I'm glad they're doing it. I just don't want to do it myself. And I think that's a perfectly valid way of having, intellectual effort be spread throughout the world. Different people should work on different things. They should be, happy with their paradigms in which they're working, trying to drive them forward. And if they turn out to be wrong, they should change their minds. But until they turn out to be wrong, until we know that they're wrong, sticking with what they're doing makes perfect sense. And that's what we're doing. That's what I'm doing. I hope we all make progress doing these things.